Hey everyone, welcome to Tech Tangents. I'm Emma, a master's student, currently neck-deep in my thesis on LLM orchestration frameworks. And today I'm super excited because we're talking about PocketFlow, which honestly couldn't have come at a better time for me. I've been wrestling with LangChain for months now, and let's just say we have a complicated relationship. PocketFlow is a 100-line minimalist LLM framework. So, Alex, you're actually a core contributor to PocketFlow, right? I'd love to hear what makes it different from the other 50 frameworks that seem to pop up every week.
Great to be here, Emma. Yeah, I've been building with PocketFlow since the early days, coming from about a decade in distributed systems. And you're right about new frameworks popping up constantly. It's getting hard to keep track. What makes PocketFlow different? Well, think of it as Lego blocks for LLM applications. While other frameworks like LangChain are comprehensive but can get, let's say, architecturally intricate over time, PocketFlow is intentionally minimalist. It's built around a single core abstraction, what we call a node, with this elegant three-step lifecycle: prepare, execute, post-process. And when you connect these nodes together into flows, directed graphs essentially, you can build surprisingly powerful applications with remarkably little code. Last week I built an entire customer support agent in about 100 lines that would have been, I don't know, maybe 600, 700 in other frameworks. There's something beautiful about that simplicity, you know?
So, Alex, I've been using LangChain for my thesis on LLM orchestration, but I keep running into these, complexity issues as my workflows get bigger. You mentioned PocketFlow has a different approach with this node concept. What exactly is a node, and how is it different from what I'm used to?
Right, so think of a node in PocketFlow as like a single-purpose worker in your workflow. It's actually beautifully simple. Each node just does one specific thing. So, for example, last week I built this text summarization system, and instead of creating this massive chain, I just had a node that handled the summarization task. It's kind of like Lego blocks for LLM apps. Each piece has one clear purpose, but you can snap them together to build something complex.
Oh, that makes sense. So it's almost like microservices versus monolithic architecture, but for LLM workflows. Wait, but how does data flow between these nodes? In LangChain, I'm always fighting with these complicated chain structures and passing stuff between components.
That's actually a great analogy. And here's the beautiful part. Every node in PocketFlow follows this really clean three-step lifecycle: prep, exec, and post. Prep is where you gather your ingredients. Read any data you need. Exec is where you do the actual work, like calling an LLM. And post is where you save your results and decide what happens next. It's kind of like baking a cake. Gather ingredients, mix and bake, then decide if you're making another dish.
I like that cake analogy. So in my summarization example, prep would be getting the text, exec would be sending it to the LLM for summarization, and post would be, what exactly? Storing the result somewhere. And how does this connect to the other nodes in my workflow?
Exactly. In post, you'd save that summary somewhere all the other nodes can access it. We use this shared dictionary-like object. But the cool part about post is you can also control the flow. Like, you can say, if the summary mentions a product, go to the product lookup node next, otherwise go to the response node. Yeah, LangChain's chains can get messy with conditionals, but with PocketFlow, you're explicitly designing your workflow graph with these directional decisions built right into the nodes themselves.
Wait, that actually solves my problem with dynamic workflows. I've been trying to create this adaptive research assistant that changes behavior based on the query type, and my if-else logic in LangChain is getting unwieldy. Could you show me what creating a simple node would look like in practice? Just so I can see the structure.
For sure. So you'd create a class that inherits from node, and then implement those three methods. Something like class summarize text node, and then you'd add your prep method that gets the text from shared storage, an exec method that calls your LLM to do the summarization, and a post method that saves the result. It's literally about 10-15 lines of code total. And the beautiful thing? You can test each piece separately, which is a nightmare in more complex frameworks. Last month I spent days debugging a LangChain pipeline, But with this structure, you know exactly where to look when something breaks.
So, Alex, I've been playing around with PocketFlow's nodes, and they're pretty neat for handling individual tasks. But I'm wondering, how do you actually connect these nodes together to build something more complex? In LangChain, we have these chain objects, but they can get pretty messy with all the callbacks and stuff.
That's where Flow comes in, Emma. Think of it as the blueprint that connects all your nodes together. You know, it's kind of like giving instructions for baking a cake. You wouldn't just hand someone a random list of tasks, you'd organize them in a specific order with decision points along the way. Like, mix ingredients, then if the batter is too thick, add more milk, then pour into a pan and bake. That organized sequence with decision points is exactly what a flow represents in PocketFlow.
Oh, so it's like a directed graph where nodes are the vertices and… Wait, how does one node know which node to go to next? Is there some kind of orchestrator keeping track of everything?
Great question. It's all based on actions. Remember how a node's post or method can return an action string? That action determines which node to execute next. The syntax is super simple. If you write node A, node B, it means if node A returns a default action, go to node EB. You can also specify named actions like node A, summarize, node C, which means if node A returns the summarize action, go to node C. It's just a few lines of code, but it gives you a ton of flexibility to create branches, loops, and complex workflows.
Wait, that actually solves one of my biggest pain points with LangChain. I was trying to build this workflow where users could input text, get a summary, and then decide whether to continue or exit. It got so complex with all the callbacks and state management. How would I build something like that in PocketFlow?
It's much simpler than you might think. You'd just need 3 nodes, an input node to collect text from the user, a summarize node to do the actual summarization, and a decision node to ask if the user wants to continue or exit. Then you connect them with actions. The input node returns a summarize action, so it goes to the summarize node. The summarize node returns a decide action, so it goes to the decision node. And the decision node can either return input to loop back to the input node or exit to end the flow. The whole thing takes maybe 20-30 lines of code, and it's super readable.
That's it? In LangChain, I was wrestling with agents, memory objects, and custom callbacks to make something similar work. It felt like I was fighting the framework rather than using it. What about more complex scenarios, like when you need to run nodes in parallel or conditionally?
Yeah, I've been there. Last week I built a system that needed to process documents, generate summaries, and answer questions, all potentially in parallel. In PocketFlow, you can just create multiple paths from a node based on different actions. For parallel processing, you can return multiple actions from a node's post, method, and the flow will execute all the corresponding paths. And here's the beautiful part. The core flow implementation is less than 100 lines of code. It's like Lego blocks for LLM apps, simple, composable pieces that you can arrange however you want. The 3-step lifecycle, prep, exec, post, is really the secret sauce that makes it all work together seamlessly.
So we've been talking about how to connect these nodes together to create workflows in PocketFlow. But I'm still wondering, how do these nodes actually share information with each other? Like, if my input node collects some text, how does my summarization node know what to summarize?
That's exactly where the shared store comes in. Think of it like a team whiteboard in an office where everyone can write notes and read what others have written. In PocketFlow, it's literally just a Python dictionary that gets passed from one node to another as your flow runs.
Wait, so it's just a regular Python dictionary? That's actually really simple. How is this different from the way LangChain handles data passing between components? Their chains always felt a bit convoluted to me.
Yeah, LangChain's chains can definitely get messy. The difference is that PocketFlow makes this shared dictionary central to the design. Each node follows a consistent pattern. They read from the store in their prep method and write to it in their post method. So your input node would write the text to the store with a key like text. Then your summarize node reads that text key before processing.
Oh, so it's like a clean separation of concerns. The node doesn't need to know where its input came from. It just looks in a standard place. That would make my thesis implementation so much cleaner. But what if I need to store complex data like embeddings or function references?
That's the beautiful part. It's just a Python dict, so you can put literally anything in there. Last week I built a RAG application where I stored document chunks, embeddings, and retrieval results all in the shared store. The vector search node wrote to it, then my LLM node read those results. No special connectors or adapters needed.
I'm starting to see why you're so passionate about this approach. In my experience with other frameworks, I've spent more time figuring out how to thread data through the pipeline than actually building the functionality. So how do you typically initialize this store?
Super simple. You just create a dictionary before running your flow. You can start with an empty one like shared, or you can pre-populate it with initial values. For instance, shared config max length 100. And since it's just a dictionary, debugging is trivial. You can print the store at any point to see exactly what's being passed around. No black boxes.
So we've been talking about how nodes can share data using that shared store pattern, which is super helpful. But I'm curious about handling really large inputs. Like, in my thesis work, I often run into situations where I need to process massive documents or datasets that just won't fit in a single LLM context window. In LangChain, I've tried using their text splitters, but it gets messy fast. How does PocketFlow approach this problem?
Oh, that's such a common pain point. You know, we actually built something specifically for this in PocketFlow called batch processing. Think of it like, imagine you're trying to eat an entire pizza. You wouldn't shove the whole thing in your mouth at once, right? You'd slice it up and eat it piece by piece. Same concept here. When your input is too big for one bite, we split it up, process each piece, and then combine the results back together.
Wait, that actually solves my problem with summarizing research papers. So it's like a MapReduce pattern. You mentioned batch processing. Is this a special kind of node, or something entirely different? And I'm guessing there must be some way to customize how the splitting and combining happens, right?
Exactly. It's very much like MapReduce, and you're spot on. We have a special type called batch node that handles this. What's cool is that it follows our familiar node lifecycle but with a twist. The prep method splits your input into chunks and returns a list. Then, exec gets called once for each chunk, like summarizing each section of your research paper. Finally, post receives all those individual results and combines them however you want. Last week I built a system that processed a 300-page legal document this way, split by paragraphs, summarized each one, then combined them with a final summary of summaries approach.
Oh, so it's like the PocketFlow philosophy distilled. That same elegant prep, exec, post pattern, but adapted for batch processing. That's much cleaner than what I've been doing with LangChain's MapReduce chains. Those get really convoluted with all the callbacks and custom handlers. Quick question though. How exactly would I implement this for, say, a document summarizer? Does the batch node handle all the iteration automatically?
Yeah, the beauty is in the simplicity. You just subclass batch node and implement those 3 methods, and PocketFlow handles all the iteration automatically. So for a document summarizer, your prep method would split the document into paragraphs or chunks, returning that list. Each chunk automatically gets sent to exec, where you'd call your LLM to summarize that single piece. Then post gets all those summaries as a list, and you can join them together, or even pass them to another LLM to create a final coherent summary. The framework manages all the plumbing. You just focus on what happens to each piece of data. It's like Lego blocks for batch processing.
That's brilliantly simple. In my experience with other frameworks, you end up writing so much boilerplate code just to handle the iteration and state management. This feels much more, I don't know, natural? Like the way you'd actually think about the problem. So just to make sure I understand, prep splits, exec processes each piece, and post combines. And PocketFlow handles passing each chunk to exec and collecting all the results for post?
That's it. You've got it exactly right. And what I love about this approach is how it makes complex workflows so much more manageable. When I was working with that legal document processor I mentioned, we actually needed to extract entities from each paragraph too. With PocketFlow, I just added another batch node that took the paragraphs, ran entity extraction on each one, and then combined the results into a searchable index. The code was surprisingly short and readable because all that batch management complexity was abstracted away. It's these little design decisions that make me excited about PocketFlow, solving real problems with minimal code.
So we've been talking about batch processing in PocketFlow, which is super useful for handling multiple items at once. But I'm curious, what happens when some operations just take forever to complete? Like, I've been building this workflow with LangChain, where API calls to OpenAI can take several seconds, and everything just sits there waiting. Is there a better approach in PocketFlow?
Oh, absolutely! This is exactly where async processing comes in. Think of it like being a chef in the kitchen. When you put water on to boil, you don't just stand there staring at it, right? You use that time to chop vegetables or prepare sauce. That's essentially what async processing does in PocketFlow. Instead of your entire program waiting idle during something slow like an API call, it can keep doing other useful work.
Wait, so it's like non-blocking operations? I've worked with Asyncio in Python before, but I always found it a bit confusing with all the event loops and coroutines. How does PocketFlow make this more approachable?
Yeah, Asyncio can definitely get overwhelming fast. What I love about PocketFlow's approach is how it wraps all that complexity into two simple concepts: AsyncNode and AsyncFlow. An async node is just like a regular node with that same clean prep exec post lifecycle we talked about earlier, but each method is asynchronous. So last week I built this recommendation system where I needed to call 3 different APIs, and instead of waiting for each sequentially, they all ran concurrently. Cut the total processing time by like 70%.
That sounds really elegant compared to what I've been doing. In my LangChain projects, I've been trying to handle async operations by, basically creating these complex callback chains that have become a nightmare to debug. So with AsyncNode, do I just add async to my methods and everything magically works? Or is there more to it?
It's pretty close to that simple. You create a class that inherits from AsyncNode instead of Node, and then implement prep-async, exec-async, and post-async methods. Behind the scenes, PocketFlow handles all the Asyncio event loop management for you. Here's the beautiful part. You can mix async nodes and regular nodes in the same flow. The system knows how to coordinate everything. For example, in my document processing pipeline, only the LLM call and database operations are async nodes. The text parsing steps are regular nodes since they're CPU-bound anyway.
Oh my god, that actually solves my thesis problem. I've been struggling with this exact issue where some parts of my workflow are I/O-bound and others are CPU-bound. So what kinds of operations would you typically make async in an LLM application? Just the model calls, or are there other places it makes sense?
Great question. The obvious ones are LLM API calls since they can take seconds to complete. But there are plenty of others. Database queries, vector store retrievals, file operations if you're processing documents, and definitely any external API calls like fetching weather data or product information. I'm working on this customer service bot that needs to look up order information while also generating responses, and making those database lookups async was a game changer for responsiveness. The users went from waiting 8 to 10 seconds for a reply to just 2-3 seconds because we're doing things concurrently now.
So we've been talking about async processing in PocketFlow, and I think I get the basic idea. But now I'm seeing parallel processing mentioned in the docs. Are these just two terms for the same thing, or is there an actual difference I should understand for my thesis?
They're definitely related, but there's a key distinction. Think of it this way. Async processing is like being a chef who can start the rice cooker and then chop vegetables while it's cooking. You're not just standing there waiting for each task to finish. Parallel processing, though, is like having 3 chefs in the kitchen, all cooking different dishes simultaneously. You're literally doing multiple operations at the same time. In PocketFlow, we have specific tools for this that can really speed up your LLM orchestration.
Oh, so async is about not wasting time while waiting, and parallel is about doing multiple things at once. That makes so much sense for LLM apps. In my thesis work, I'm constantly hitting bottlenecks when I need to process a bunch of documents through an LLM. With LangChain, I've been writing these nested for loops with Asyncio gather calls, and honestly, it gets really messy really fast. Does PocketFlow have a cleaner approach?
Yeah, LangChain's chains can get unwieldy with that pattern. We've all been there with the Asyncio gather hell. PocketFlow handles this with two main classes. First, there's Async parallel batch node. Last week I built a news analyzer that needed to summarize about 50 different articles. Instead of processing them sequentially, I just created this node that automatically handles all the parallelization. You implement three methods: prep myAsync to get your batch of items, exec myAsync for processing each one, and post myAsync to collect all results. PocketFlow handles all the complex parallelization logic behind the scenes.
Wait, that actually solves my problem with document processing. So I just return my list of documents from prep.async, then define the LLM call in exec.async, and finally collect everything in post.async? That seems way cleaner than what I've been doing. But what if I have a more complex pipeline for each document? Like parsing, summarizing, fact extraction. Would I need to cram all that into the exec.async method?
Great question. That's where the second class comes in, Async parallel batch flow. And here's the beautiful part. It lets you run an entire flow in parallel for each item. So you can build out that complex document pipeline as its own flow with multiple nodes, and then Async parallel batch flow will run the whole thing in parallel for each document. It's like having a team of workers, each following the same process but on different inputs. And it's all controlled with the same simple three-method pattern, no manual thread management or complex concurrency code.
That's actually brilliant. The framework takes care of all the parallelization complexity, but I still get to define my logic in this clean, sequential way. I'm curious, though, in real-world applications, how does this perform? I've run into memory issues before when trying to process too many documents at once with other frameworks.
That's a totally valid concern. In production, we found that you need to be thoughtful about resource constraints. The good news is that PocketFlow lets you control the degree of parallelism. You can tell Async parallel batch node to process, say only 5 items at a time instead of all 50. This gives you the speed boost of parallelism without overwhelming your system or hitting API rate limits. I'm running a system that processes thousands of documents daily using this pattern. The nice thing is you can tune it based on your specific hardware and requirements without changing your core business logic. It's much more manageable than trying to build custom throttling logic yourself.
So with parallel processing in PocketFlow, you can basically run multiple operations at the same time, which is super useful for handling independent tasks. But what about when you have a complex process with multiple steps that need to happen in sequence? Like, I'm thinking about my thesis project, where I need to retrieve data, then analyze it, then generate a response based on the analysis.
That's a perfect segue into what we call the workflow pattern in PocketFlow. It's basically designed for exactly that kind of situation, when you need to break down a complex task into a sequence of simpler ones. Just like following a recipe to bake a cake rather than saying, just make cake in one step, you know?
Oh, so it's like creating a pipeline? I've tried doing something similar with LangChain's sequential chains, but it got really messy really fast. The code became this tangled web of callbacks, and I lost track of what was happening where.
Yeah, exactly. It is like a pipeline. And I feel your pain with LangChain. Those chains can definitely get unwieldy. The workflow pattern in PocketFlow is more… how do I put this? It's more composable. Each node in the workflow has a clear job. It takes input from the previous step, does its specific thing, and passes results to the next node.
Wait, that actually solves my problem with context windows. I've been trying to jam everything into one massive prompt, and then the LLM gets confused or goes off track. So instead, I could have one node generate an outline, another node write the content based on that outline, and maybe a third node refine everything. Kind of like breaking down the writing process.
You got it! That's exactly the approach I used last week for a client project. We built a content generation system where one node created an outline, another expanded each section into full paragraphs, and a third one polished the style to match their brand voice. And here's the beautiful part. Because each step has a specific purpose, we could easily swap in different approaches for any step without messing with the rest of the workflow.
That's so much cleaner than what I've been doing. But I'm curious, how does the data actually flow between these nodes? In LangChain, I spent half my time just figuring out how to get the output from one chain formatted correctly to be the input for the next chain.
That's where PocketFlow's three-step lifecycle really shines. Remember how each node has prep, exec, and post methods? Well, in the post method of your first node, you store the result in the shared state. Then in the prep method of your second node, you grab what you need from that shared state. It's like having a workspace where each specialist can pick up exactly what they need from the previous person's work. No complex mappings or formatters needed.
So, Alex, we talked about the workflow pattern last time, breaking tasks into those sequential steps. But I've been thinking, what happens when we need something more, adaptive? Like when the system needs to figure out its own path based on what it discovers. Is that where this agent pattern comes in?
Exactly. You've hit the nail on the head, Emma. The agent pattern is basically for when you need your system to think on its feet. So instead of saying, do A, then B, then C, like in a workflow, you're essentially saying, here's your goal, figure out how to get there. It's like, you know how when you ask a friend to research something, you don't micromanage every step, right? You trust them to decide whether to Google something, check a book, or maybe ask someone else.
Oh, wait, that makes so much sense. So it's the difference between me giving my research assistant explicit instructions versus just saying, find everything you can about PocketFlow and letting them figure out the how. So in practical terms, how does the workflow pattern and agent pattern actually differ in implementation? I'm trying to visualize the architecture here.
Great question. Think of it like this. A workflow pattern is like following a recipe. Step 1. Chop onions. Step 2. Heat pan. Step 3. Add oil. It's linear and predetermined. But the agent pattern is more like a chef creating a new dish. They taste, think, needs more salt, add some, taste again, maybe decide to add herbs instead. It's this continuous loop of think, decide, act, evaluate. In PocketFlow, we implement this with 3 key components. A decision node that acts as the brain deciding what to do next, action nodes that actually perform tasks like searching or generating text, and context management that maintains memory of what's happened so far. The beauty is how simple this becomes with our node abstraction. The whole thing can be implemented in just a few dozen lines of code.
So we were just talking about these agent patterns, which are super fascinating for orchestrating LLMs to take actions. But I've been wondering, what do you do when your agent needs access to specific information that might not be in the LLM's training data? Like, company policies or recent research papers that came out after the model's training cutoff.
That's exactly where RAG comes in. RAG stands for Retrieval Augmented Generation. And it's kind of like, you know how you might have a really smart friend who knows a lot, but they still need to look things up sometimes? RAG is basically giving your LLM the ability to look things up before answering. Instead of just generating responses from what it was trained on, it first retrieves relevant information from a knowledge base and then uses that to generate a more accurate, up-to-date response.
Oh, that makes sense. So it's like the difference between me writing an essay purely from memory versus writing it after doing research in the library. How is this different from just fine-tuning a model on specific data? Because I've been experimenting with fine-tuning for my thesis, and it's a bit of a pain, honestly. Wait, that actually solves a problem I've been having in my thesis. I've been trying to make my LLM answer questions about research papers that came out after its training cutoff. I was going down this whole complicated path with fine-tuning, but this sounds much more practical. So how does RAG actually work under the hood? What's the architecture like?
I love seeing that light bulb moment. You can literally see the aha on your face. RAG works in 2 main phases. First, there's an offline phase where you process your documents. You collect them, split them into manageable chunks, convert those chunks into vectors called embeddings, and store them in a searchable index. Think of it as building your library and creating a really good catalog system. Then there's the online phase that happens each time someone asks a question. You convert the question into the same vector space, find the most similar documents in your index, and send both the question and those retrieved documents to the LLM to generate an answer. The beauty of this approach is that you only do the heavy lifting of processing documents once, and then each query is relatively lightweight.
That makes a lot of sense. How would you implement something like this in PocketFlow? I've tried building RAG systems with LangChain, but they can get pretty complex pretty quickly. I end up with these massive chains that are hard to debug and maintain.
Oh, I feel your pain with LangChain. Don't get me wrong, it's powerful, but yeah, those chains can turn into spaghetti code real fast. In PocketFlow, we break it down into simple, composable nodes. You'd create nodes for each step of the process. One for chunking documents, one for creating embeddings, one for retrieval, and one for generation. Each node follows that same prep-exec-post lifecycle we talked about earlier. And here's the beautiful part. Because everything is just a simple node with the same interface, you can easily swap components, add monitoring, or run parts in parallel without changing your core logic. Last week, I built a RAG system for our technical documentation in about 50 lines of code compared to hundreds in other frameworks.
So we've been talking about RAG for enhancing LLM responses with relevant information, which is super helpful for my thesis work. But I'm wondering, what happens when you need to process really large data sets? Like, I tried running some RAG pipelines on a corpus of research papers, and everything just got so slow. Is there a standard pattern for scaling this kind of processing in PocketFlow?
That's exactly the kind of problem the MapReduce pattern solves. Think of it like, you know how when you're throwing a big dinner party, you might ask friends to each bring a dish instead of cooking everything yourself? MapReduce works the same way. You break a big task into smaller chunks that can be processed independently, that's the map phase, and then combine all the results at the end, that's the reduce phase. PocketFlow makes this super easy to implement with just a few lines of code.
Oh, so it's kind of like parallel processing but with a specific structure to it? Wait, is this similar to the MapReduce framework from Big Data? I remember learning about Hadoop in my distributed systems class, but that seemed way more complex than what you're describing.
You've got it. It's inspired by the same concept, but much more lightweight. Let me give you a real example. Last month, I built a system that needed to analyze about 50 legal contracts for compliance issues. Instead of sending all 50 to the LLM at once, which would be expensive and probably exceed context limits, I used MapReduce in PocketFlow. Each contract was processed independently by the LLM to extract potential issues, and then a final reduce step compiled everything into a summary report with risk categories. The whole thing took about 30 lines of code, compared to hundreds in other frameworks I've used.
That sounds incredibly useful. In LangChain, I'd probably need to set up a complex chain with callbacks and custom handlers to achieve something similar. How exactly does PocketFlow implement this? Does it use that node abstraction you mentioned earlier?
Yeah, and here's the beautiful part. It leverages the same node pattern we've been using all along. For the map phase, you typically use a batch node that knows how to break your dataset into chunks. The prep method returns your list of items to process, then exec runs on each item independently, and PocketFlow can even parallelize this automatically. For the reduce phase, you create another node that takes all those individual results and combines them. The whole flow is just chef's kiss. So clean and explicit. No hidden magic. No complex configuration.
Wait, that actually solves a huge problem I've been having with my thesis implementation. I've been trying to analyze how different prompting strategies affect different types of questions across multiple models, and my code got really messy trying to manage all the combinations. So if I understand correctly, I could use the map phase to process each combination in parallel, and then the reduce phase to compile all the statistics and insights.
Exactly. And the best part is how composable it is. For your thesis, you could even nest MapReduce patterns, like map over different models, then for each model, map over different prompting strategies, then reduce the results at each level. I did something similar when benchmarking different embedding models. The outer map handled different models, the inner map processed different dataset slices, and the reduce steps compiled statistics at each level. It's like Lego blocks you can arrange however you need, without getting lost in callback hell or trying to debug someone else's abstraction.